Welcome back to ControlX Automation. I'm Akhil and I want to start today with a question that sounds simple but has a very specific and important engineering answer. Why is a transformer rated in kVA and not kilowatts? If you know the full answer and the physics behind it, then you're ahead of a lot of engineers already. If you don't, by the end of this video, you will. And you will never look at a transformer nameplate the same way again. In today's tutorial, we'll talk about industrial control transformers, specifically the types of control transformers and why they are fundamentally different from other transformer types, the standards that govern them, how to properly size them for real industrial loads. So we'll be diving into the engineering design calculations for both single-phase and three-phase applications, also how to size your primary and secondary overcurrent protection as per code. And we'll look into the various transformer configurations. We'll touch a little bit on the topic of isolation transformers and when you actually need one. Finally, we'll learn how to read transformer nameplates and figure out exactly what it's telling you. So let's get started. Let's start with the basics. What is a control transformer? A control transformer, also called a machine tool transformer or industrial control transformer, is a dry type single-phase or three-phase transformer specifically engineered to supply a stable voltage source to AC control circuits in industrial machinery, motor control centers, and control panels. Its electrical symbol looks like this. Here I'm showing you a single-phase transformer, which means it takes a single-phase voltage applied on the primary and transforms it to a different voltage on the secondary through the principle of electromagnetic induction. In industrial control applications, its main function is to step down line voltage, for example 480 volt or 600 volt, to a lower control voltage, typically 120 volts in North America and 220 volts in IEC markets. The purpose is to power electronic components like PLCs, sensors, network switches, and electromagnetic devices like contactors, relays, solenoid valves, as well as indicating devices like pilot lights and other AC and DC components. You may ask, why not just use a general purpose transformer? What's so special about a control transformer? You see, control transformers are not the same as general purpose transformers. They are specifically designed to handle the high inrush current produced when multiple inductive loads like contactor coils and solenoid valves energize simultaneously. A general purpose transformer would exhibit excessive secondary voltage sag under these inrush conditions, causing coils to drop out or fail to pull in. Control transformers achieve this by using higher core flux density, lower impedance for tighter regulation under inrush, and they also employ a heavier gauge primary and secondary windings rated for inrush surge. They are designed for continuous duty at rated power and are available in a wide standard power rating range, typically anywhere from 50 VA to 10,000 VA for most control panel applications. Let's look at the types of transformers commonly used in industrial control panels. The most common type is the single-phase transformer. It is generally used to step down from the mains voltage to a lower voltage used for control systems like 110 or 120 volts, which is common in US and Canada. This table lists the typical specifications for a single-phase control transformer. Feel free to pause here to review it in detail. Three-phase transformers are used with larger control circuits when the VA demands needs to be balanced across all three phases, or when the connected load is inherently three-phase like motors and high-powered heaters. This table lists the typical configurations for three-phase transformers. The delta-delta configuration is where both primary and secondary phase windings are arranged in a delta configuration, as shown. The corners of the triangle are the phase connection points. This configuration is commonly used for step down, and the secondary voltages are in phase with the primary due to no phase shift. Also, this configuration provides three-phase power using only 3 wires and does not require a neutral return path. However, the most common configuration is the delta Y configuration, where the secondary windings are set up in a Y arrangement as shown. This configuration provides a neutral return path at the center. Voltages measured with respect to neutral are called phase voltages, and the voltages measured across the lines are called line voltages. In case of delta windings, the line and phase voltages are the same. The distinction only applies to Y windings. This equation shows a relationship between the phase voltage in a three-phase system with a neutral. The line voltage is always higher than the phase voltage by a factor of square root of 3. If you're curious about the physics behind this equation and where that square root of 3 comes from, let me know in the comments below and I can cover that in a separate video. Lastly, we have the Y delta configuration. This is uncommon in controls. I have not seen one of these yet. A typical use for a three-phase transformer in controls is for stepping down from mains facility voltage of a three-phase 480 volts or 600 volts down to 208 volts if measured line to line, or 120 volts if measured line to neutral. Typical power ratings for controls use is between 1 kVA to 30 kVA. Another type of transformer used in industrial applications is the isolation transformer. While not strictly a control transformer, it is still widely used in certain applications where isolation is required from the facility mains power. These are typically three-phase transformers with a 1:1 ratio, which means that the secondary voltage is the same as primary, which is usually the case. However, in certain applications, it could also step down, for example, from 600 volt feed to 480 volt feed. They're usually of higher power rating to supply the machine or process that it is used for. The key purpose of an isolation transformer is to create a galvanic separation or isolation, hence the name, between the power source and the load, meaning there is no direct conductive path between the primary and secondary circuits. One benefit of this separation is that it reduces electric shock hazards by ensuring that the secondary circuit is floating and not directly connected to ground. So accidental contact with live wire does not complete a circuit through a person, although this requires that the secondary neutral is not grounded. Isolation transformers are widely used in environments where personal safety is critical, such as hospitals, laboratories, and industrial settings. By isolating the secondary circuit, they protect the individual from electric shocks by preventing the direct flow of current to the person touching a single live wire. However, I must point out that if you touch two live phases, then you're still cooked. Another important purpose is mitigating electrical noise and interference. Power lines often carry unwanted spikes, humps, and transients from other devices. The isolation transformers separate windings and magnetic coupling, block high-frequency noise and ground loop interference, providing a much cleaner and more stable power supply source for sensitive electronics like computers, medical devices, and lab instruments. Isolation transformers also reduce voltage spikes and transients caused by lightning, static electricity, or sudden load changes. The inductive properties of the transformer windings kind of acts like a filter which prevents rapid voltage changes from directly reaching the load, thereby protecting connected equipment from potential damage. To better understand how isolation transformers work, it is important to understand the concept of grounded and ungrounded secondary. When the transformer secondary is grounded by bonding the neutral on a Y secondary to ground, it is called a grounded system, and the phase voltages are referenced to ground. This prevents the secondary voltages from flowing. Here I show one of the three voltages. Notice how it is centered or fixed on the x-axis. This means that a single ground fault on any phase causes an immediate short circuit, resulting in a blown fuse or breaker trip. If a person comes in contact with a live phase, the circuit gets completed through the person's body, resulting in an electric shock. On the other hand, we can get an ungrounded system by removing the secondary ground connection from the neutral on a Y secondary. This results in a floating output that is not referenced to ground. Here I am only showing one of the three phases, but all three phases are floating with respect to the ground. This is called a floating separately derived system. Note that the term ungrounded only refers to whether the transformer neutral is bonded to ground or not. The transformer frame and enclosure are still grounded as per applicable standards. A person standing on the floor is at earth potential, electrically speaking. Touching one phase does not complete the electrical circuit back to the neutral or another phase, as long as he's only in contact with one phase. When a person touches a floating phase, their body provides a low resistance path to ground, which pulls that phase voltage down. Now if you measure the RMS voltage between that phase to ground, it will be close to 0 volts. So why doesn't the person experience an electric shock? This is because the net voltage difference between his body and the phase is almost 0, so no current flows through his body. However, there's still some capacitive charging current, which is typically very small, rarely enough to cause an electric shock. Now that the system has become a grounded system with one grounded phase, a second ground fault anywhere else causes the phase-to-phase short, which can result in a hazardous condition. This is why ungrounded systems must have ground fault monitoring, like this device from Bender. Let me know in the comments below if you need more information about this device or you're curious about how it works. You must have heard this question asked at some point. Why transformers are rated in VA and not watts? Almost every device is rated in watts. For example, light bulbs, motors, heaters, etc. all have their rated power listed in watts. So why not transformers? This is one of the most fundamental concepts in power systems engineering and directly underpins every transformer sizing calculations. The answer lies in the physics of how transformers and AC circuits in general actually work. To grasp this concept, we must first understand the three types of AC power. In any AC circuits with reactive elements like inductors and capacitors, power takes three distinct forms. First is the real power, P, with units of watts. This is the power actually consumed and converted to work or heat by the load. It is used to turn a motor, heat an element or a light bulb. Resistive loads like heaters and incandescent lamps consume only real power. However, not every load is purely resistive. Some loads like induction motors, relays, contactors, solenoid valves, etc. also have another electrical property called inductance. Similarly, capacitive loads have a property called capacitance. Together, these types of loads are called reactive loads. These reactive devices store energy in magnetic or electric fields and then push it back into the system every cycle. This back and forth exchange does not produce useful work, but still loads the transformer that is supplying the power. This is the reactive power Q, and its unit of measure is VA reactive. The total power that the source and the transformer supplying it must actually deliver is the apparent power S. It is the vector sum of the real and reactive powers, and it equals the simple product of RMS voltage and RMS current. Hence, its unit of measure is the volt ampere, or VA for short. The relationship between P, Q, and S can be graphically represented by what is known in electrical engineering as the power triangle. With purely resistive loads like a heater, for example, there is no reactive component Q, and the angle phi is almost zero. Thus, the hypotenuse of the triangle overlaps with the base, which means that the apparent power S supplied by the transformer is equal to the power P consumed by the resistive load. We can also see this from the equation for P. When phi equals 0, the cosine of that angle is 1. Thus, the real power P equal to VI, which is the same as the apparent power S. Another thing I forgot to mention is that the angle phi represents the phase difference between the AC voltage and current. So with a resistive load, the angle being 0 implies that the current is in phase with the voltage. However, with real-world loads, there is always some reactance, mostly inductance from the coils and the length of wires, which means that the angle phi is never exactly 0. This results in a net positive reactive component Q, and the transformer must now supply additional VA to account for the reactive component. The actual work, however, is still being done by the real power P, but now the transformer has to supply additional VA to account for the reactive component of the load, which does no real work. The higher the angle phi, the more apparent power must be supplied by the transformer. Therefore, it is crucial to keep that angle small. The cos phi term in the equation P has a special name and is called power factor. Ideally, we want unity power factor by reducing that reactive component. The relationship between the three powers is given by Pythagoras' equation for a right triangle, S square equal to P square plus Q squared. And the power factor can be calculated by using this formula. In real industrial loads, power factor is usually between 0.3 and 0.9, depending on load types. This brings us back to our question: why transformers are rated in VA and not watts? As you've seen, the transformer has no way of knowing what kind of load is being connected to it. The load can have any power factor between 0 and 1. All it is supplying are the volt amps, and the real power consumed by the load in watts is determined by that load's power factor. Hence, the transformer can only be rated in volt amps and not in watts. The IEEE and IEC transformer standards universally rate transformers in VA or kVA for this exact reason. VA rating is independent of load type. The same transformer can supply resistive heaters, inductive motors, starters, capacitive power factor correction banks, or any combination. The VA limit applies equally to all. A watt rating would require a different nameplate for every power factor. VA is additive across loads, so the total VA demand of a mixed load group is calculable from the power triangle. Watts of different power factors cannot be simply added without also tracking the reactive components of each load. The transformer has no power factor. The transformer itself is not a load, it's a coupling device. It merely transfers whatever combination of real and reactive powers that the load demands, subject only to its volt amp capacity and turns ratio. Characterizing a transformer by watts implies it does work. It does not. It merely transfers power. This is why every load entry in the sizing methodology, which we will discuss shortly, uses VA. AC contactor coils have a power factor between 0.3 to 0.5. If you sized for watts, you would grossly underestimate the transformer current demand, since watts does not account for the reactive component from the power triangle. Switched mode power supplies, or SMPS, have near unity displacement power factor, but may have significant harmonic current content. Thus, their VA does not equal watts in a strict sense, and their VA demand on the transformer exceeds their watt consumption. The vector inrush formula shown here is itself a power triangle calculation. The inrush VA is largely reactive. The sealed non-inrush VA has a real power component P. This formula correctly adds them as perpendicular vectors, which is only possible because we are working in VA throughout. This will become clear later when we go through calculation examples. The key takeaway from this is any transformer sizing exercise that begins with watts and fails to convert to VA using the actual load power factors will produce an undersized transformer and a panel that overheats and fails. If you're getting value from this tutorial, then please take a moment to subscribe to the channel and hit that like button. It really helps the channel grow and allows me to keep producing more engineering content for you. Alright, now let's get into the fun stuff. In this section, let's look at some of the key engineering design considerations when it comes to sizing a control transformer for your application. Since control transformers are mostly used with industrial control system applications, the loads it will be serving include electromagnetic components like contactors, relays, solenoid valves, climate control devices like air conditioners, blower fans, pump motors, and the like. Before sizing a transformer, classify every load connected to the secondary. Always use the load's VA rating and never watts for transformer sizing. A power factor of less than 1 means the transformer must supply more apparent power than the load's real power, as we have seen earlier. This table lists only AC loads that could be supplied by the transformer. Many modern control panels will use DC components like LED indicators, PLCs, network switches, etc. These are supplied by switch mode power supplies, and those loads can be excluded since the power supply that's supplying them is already accounted for in the transformer sizing consideration. One thing of importance to be noted is that electromagnetic switching devices have dual VA ratings. They have sealed VA and inrush VA ratings. Sealed VA is the steady state VA that a coil draws once it's energized and the magnetic circuit has fully established. Inrush VA is the initial surge VA that the coil draws the moment it's energized, before the magnetic field stabilizes, and it's often 5 to 10 times higher than the steady state rating. The inrush duration is quite small, typically 25 to 200 milliseconds, depending on the coil design and load. This becomes critical for AC components which energize on power up. The transformer must be sized properly to account for the inrush VA of these components if they energize simultaneously. Now, this may not always be the case, so the sizing calculation must take your application into consideration. If the transformer can't supply that momentary surge, this results in a voltage drop and the device might fail to pull in or start chattering. In any case, this will lead to unpredictable machine behavior. IC contractors per IC 60947 publish the pickup or inrush and the holding or sealed VA ratings on their datasheets. So make sure to take those into considerations in the design calculations. Let's look at the step-by-step methodology. The first step is to compile the load list and list every load, its sealed VA and its inrush VA if applicable. Remember, this only applies to electromagnetic switching devices, as we have learned. Next, sum up all the sealed VA values for the connected loads. Then account for inrush using the vector addition formula that we saw earlier. You may ask, why not just add the sealed and inrush VA instead of using this formula? That's because at the moment of energization, the inrush coil currents are predominantly reactive, resulting in near 90-degree lagging power factor. The sealed loads like SMPS and resistive devices are largely resistive and the current is in phase. Because these two current components are approximately 90 degrees out of phase with each other, they add as vectors and not scalars. Scalar addition would significantly overestimate the transformer VA requirement. It is always a good design practice to apply a minimum of 20 to 25% safety margin to account for future load additions, ambient temperature derating, and voltage regulation under load. After you have arrived at the theoretical transformer size, we select the next standard VA available from the manufacturer. Okay, let's look at some examples. We'll start with a simple single-phase transformer sizing calculation. Step 1 was to compile the load list. So here's the list of loads for my small control panel. Here I've identified the electromagnetic switching loads and their inrush VA is listed in addition to their sealed VA. I got these specs from their respective datasheets. From the list, we can see my total sealed VA is 309. This is the continuous rating that the transformer must supply during steady state operation. For inrush consideration, the worst case scenario is all contactors and relays energized simultaneously, which gives us a total inrush VA of 920. When the system first powers up, the transformer sees this inrush VA plus the sealed VA of the remaining components highlighted here, totaling 189 VA. Now we can calculate the application VA using the vector addition formula, which gives us 939 VA. Then we apply a safety factor on top. I'll go with 25% margin to get the design VA of 1174 VA. For our transformer selection, I'll pick the next available standard size, which is 1500 VA or 1.5 kVA 480 to 120 step-down transformer. If we had sized our transformer based on the total sealed VA power rating of 309 VA and picked, let's say, a 500 VA transformer, we would be grossly undersized and the system would fail under the simultaneously coil inrush. That's why we have to use the vector addition formula. Now that the transformer size has been determined, we need to incorporate protection on both the transformer primary and secondary. Let's start with the primary side protection. The full load primary current when the transformer is loaded to 1500 VA is the transformer rating divided by the primary voltage, which gives us 3.125 amps. Since I will be providing both primary and secondary circuit protection to comply with UL 508A, I will refer to table in NEC 450.3b. The primary side fuse protection needs to be sized at 250% of rated current. This gives us a fuse rating of 7.81 amps. I'll go with the next standard fuse size and pick a 7 amp class CC time delay fuse. Using time delay fuse type handles transformer magnetizing inrush without nuisance tripping. Now you may be wondering, why did I go with a smaller fuse size than the calculated value? NEC section 450.3b states that if the calculated overcurrent protection device rating does not correspond to a standard fuse size, then we must round down to the next standard size, not up. This is the opposite of the general NEC 240.3b, a rounding rule that applies to conductor ampacity, and it catches most engineers off guard, including myself. The transformer primary OCPD is always the next standard size at or below the calculated maximum. Now that we have determined the overcurrent protection device sizing, we need to connect them using appropriate sized conductors. For that, we'll refer to NEC 310, which is a section of the United States National Electric Code of NFPA 70 that governs conductors for general wiring, including their materials, insulation types, ampacity ratings, temperature limits, and installation conditions. Canadian viewers must reference the CEC or Canadian Electric Code CSA C22.1. Per NEC 310 and UL 508A, conductors must be sized at minimum 125% of continuous current, since all transformer loads are considered continuous. This table summarizes the calculated ampacities for conductor sizing and the appropriate wire gauge for both the transformer primary and secondary circuits. The allowable conductor size is taken from NEC table 310.16. I will be using 75-degree conductors, and looks like 14-gauge wire will be suitable for both primary and secondary circuits. For our second example, let's look at a slightly larger control panel. Here's my load list for the system. These are my electromagnetic switching loads. Let's do the inrush analysis just like last time. This is my total inrush VA. The sealed VA of the other components is calculated. Next, we calculate the application VA using the vector addition formula just like last time. Then we apply a safety factor of 25%. For our transformer selection, I'll pick the next available standard size, which gives us 5 kVA 480 to 120 step-down transformer. Next, we do the overcurrent protection devices. Let's calculate the primary fuse size first. The primary voltage is calculated based on the transformer power rating and primary voltage. Referring to the table on NEC 450.3b, we apply the 250% multiplier to determine the OCPD rating. Finally, we pick the closest standard fuse size. Similarly, we calculate the secondary current. From NEC 450.3b, we use the 125% multiplier since our calculated secondary current exceeds 9 amps, and we get the maximum secondary fuse size. Finally, we pick the closest standard fuse size. Here I chose a 50 amp class J time delay fuse. Now that we have our primary and secondary full load currents calculated, we can refer to the NEC table 310.16 and select the appropriate conductors. The most common industrial control panel arrangement uses a single-phase control transformer. If the mains feed to the control panel is 3-phase, then 2 phases of the 3-phase supply is connected to the transformer primary. In this example, 2 of the 3 phases L1 and L2 provide the 480 volts to the transformer primary, and we get single-phase 120 volt on the secondary, which supplies the single-phase loads in our panel. However, a true 3-phase control transformer is warranted when the secondary must supply a mix of both single-phase and 3-phase loads. This transformer can supply 3-phase loads directly on the secondary, example 208-volt 3-phase servo drives, VFDs, small motors, heating elements, etc. It can also supply single-phase 120-volt loads provided that the transformer neutral is grounded as shown. To work with 3-phase systems, we must first review some fundamental formulas. First one, in no particular order, shows how to calculate the line current if apparent power or kVA rating and the line-to-line voltages are known. This one is a rearranged formula to calculate the apparent power or kVA rating if the line voltage and current are known. This one gives us the phase voltage if the line voltage is known. As an example, for 3-phase 208-volt system, the line voltage is 208 volts. This gives us a phase voltage of 120 volts if measured between any phase and the neutral. Finally, if the total apparent power or kVA of a balanced system is known, the per phase apparent power rating is simply 1/3 of it. Before applying the sizing formula, we must categorize the loads into 2 groups. In Group A, we categorize all 3-phase balanced loads. Balanced loads means that they draw equal currents from all the 3 phases. Their VA contribution distributes evenly across all 3 transformer windings. Examples are 3-phase servo drives and VFDs, 3-phase resistive heaters, small 3-phase motors, blowers, fans, etc. Direct online or fed directly from the transformer secondary. In Group B, we have single-phase loads, which must be distributed equally across the 3 phases for balance. These loads are connected phase to neutral and load only one winding at a time. To avoid winding imbalance and circulating currents in the delta primary, the designer should try to distribute the loads as evenly as possible across the three phases. Examples of single phase loads are control circuits like contactors, solenoids, switch mode power supplies, HMI panels, cooling fans, lighting, etc. As a general rule, the sum of single phase loads on any one phase should not deviate more than approximately 10% from the average single phase load per phase. Significant imbalance causes unequal transformer winding temperatures and causes other issues like increased circulating currents in the delta winding, which ultimately reduces the transformer life. For the three-phase transformer sizing calculations, step 1 is to determine the total application VA, which is calculated using a vector addition formula just like before, but on a total system VA basis. This will be clear when we do an example later. Next, we apply a safety margin to the calculated VA. Then we select the closest standard size available from the manufacturer. Finally, perform a phase balance check to make sure our loads are balanced across all three phases and that the maximum per phase load is well below 1/3 of the transformer kVA rating. This ensures that we don't overload any single phase more than the other phases. It may not be possible to balance the loads exactly, but we should try our best to get as close as possible. Performing a phase balance check will show us how much each phase winding has been loaded. Again, this will become clearer when we go through an example. Okay, let's apply what we have learned with this example. My control panel is fed with 480 volts, but my loads require both single phase 120 as well as three phase 208 volts. We need to calculate the size of the step-down transformer for this panel. I've compiled the load list from my control panel, which has mixed loads as you can see. The loads include electromagnetic switching devices rated for single phase 120 volts, some non-inrush 120 volt consumers, as well as three-phase servo drives and heater banks. This table lists the total sealed VA for all consumers and inrush VA for the electromagnetic devices. We have all the information to calculate the required transformer size. First, we calculate the total inrush VA for the contactors, solenoid valves, and relays. Then we calculate the total sealed VA for the remaining non-inrush components. Now apply the vector addition formula to calculate the application VA just as we did before. Finally, I apply a 25% safety factor and we get the required transformer size for our application. I'll pick the closest standard size from the manufacturer's catalog that is larger than the calculated VA, and we get our transformer. Next step is to perform the phase balance check. This ensures that we are not overloading any single phase. To do that, we need to calculate the per phase loading on each phase. For the three phase, we just sum up all the three phase loads and divide by 3. This gives us the per phase VA for the three phase loads. Now for the single phase loads, they need to be distributed equally among the three phases of the transformer. So we sum up all the single phase sealed VAs and divide by 3 to get the ideal distribution across the three phases. Next, we add them up to get the total per phase loading. Now our transformer delivers 7,500 VA in total. So its per phase VA is the rated VA divided by 3, which gives us 2,500 VA per phase. Looks like our loading is well below the transformer's per phase VA. Therefore, our loading factor comes out to 62% of rated VA. This looks acceptable. This only works if during the electrical design, care is taken to distribute the single phase loads across the three phases such that we do not exceed the calculated 249 VA phase by a lot. If you look at our load list, the SMPS requires 240 VA at full load. That means each SMPS can be connected to lines L1 and L2, and the remaining single phase loads can be connected to line L3, which will give us almost balanced loading. Now what happens if instead of distributing the loads, we put all single phase loads on one phase? Let's check the worst case scenario. And looks like the total VA brings us to 82% of the transformer rated, which in this case will still work. Although this uneven loading will cause unequal copper losses between the windings, resulting in thermal stress and accelerated degradation on that one winding, which will affect the transformer life in the long run. Next step in the design process is the transformer primary and secondary protection. Let's start with the primary side protection. First, I'll calculate the primary full load current. Since I will also be providing secondary overcurrent protection, therefore I'll use a safety factor of 250%, which gives us 22.55 amp fuse rating. Rounding down to the nearest standard size gives us 20 amp. I'll go with Class J time delay fuses in a 3-pole fusible disconnect switch or 3-pole fuse holder with 320 amp fuses. Next is the secondary protection. Let's calculate the secondary full load current. I'll apply a safety factor of 25%, which gives us 26.02 amps for the fuse rating. Rounding it down to the nearest standard size gives us 25 amps. I will go with Class J time delay fuses in a 3-pole fuse holder with 3 25 amp fuses. Also, we must ensure that all single-phase branch circuits between the phase and neutral must also have single-pole fuse protection for those branches. If using 14-gauge conductors, the maximum allowable fuse is 15 amps per NEC 450.3. Now that we have our primary and secondary full load currents calculated, we can refer to NEC table 310.16 and select the appropriate conductors as I have shown in this table. For grounding, the neutral, which is the star center point, is to be bonded to the equipment grounding conductor. Grounding the secondary neutral ensures that the output voltage is not floating, as we discussed earlier. The neutral conductor is an insulated conductor which could either be white or gray, and never use bare neutral inside a panel enclosure. For the delta secondary, there is no neutral, so no secondary grounding is available unless one phase is grounded. This configuration is called corner grounded delta and is rare and not recommended for new installations. If the secondary is left ungrounded, it is a good practice to install an IMD or insulation monitoring device to detect the first fault condition. A transformer produces heat because electrical energy is never transferred perfectly. Some of it is lost as copper losses and some as core losses. This image shows a side-by-side heat map using thermal imaging software. As you can see, the transformer can get really toasty depending on its loading. Copper losses, also known as load losses, come from the resistance of the windings when current flows through it and generates heat. Hence, it's also called I²R losses. Core losses, on the other hand, occur even with no load and are made of hysteresis loss, which is caused by the magnetic domains flipping direction each cycle, and eddy current loss, which is caused by circulating currents in the iron core. Eddy current loss increases with frequency and flux density. Together, these losses convert part of the electrical input into heat, which is why a transformer warms up at no load and gets hotter as the load increases. The total heat dissipated due to losses is given by this equation, where eta is the efficiency of the transformer. This is usually mentioned on the transformer nameplate or its datasheet. This table shows typical transformer efficiencies and heat dissipated in watts for a few common transformer sizes. Again, this varies from manufacturer to manufacturer and other design specs. Also, these are full load values. At typical control panel loading, which is often 40 to 70% of transformer rating, the actual heat dissipation might be lower, but core losses are constant regardless of load. What is the thermal impact of all heat sources inside the enclosure? Other than the transformer, we may have other components like VFDs, power supplies, motor starters, etc., which all contribute to the overall heat production inside the enclosure, and their thermal impact must be accounted for. To estimate the temperature rise inside a painted steel enclosure without forced ventilation, determine the total surface area exposed to air using the enclosure dimensions. Use the heat transfer coefficient for painted steel, which is 5.5 watt per meter square Kelvin. Apply this formula, where Q is the dissipated heat in watts, H is the transfer coefficient, A is the total surface area, and delta T is the temperature difference between the enclosure interior and ambient air. Finally, include a safety margin, typically 25% to account for variations in internal layout, airflow, and environmental conditions. For most panels containing a transformer more than 500 VA plus other heat sources, some form of thermal management like forced ventilation fan is required. Now let's talk about transformer mounting locations inside the control panel. I usually prefer to have the transformer mounted close to the top part of the control panel for a couple of reasons. Number one, heat rises. Placing the transformer along with other similar components like VFDs, motor starters, and power supplies at the top keeps heat away from sensitive electronic components down below. Transformers in particular generate continuous heat from the copper and core losses. Since heat naturally rises, mounting the transformer at the top prevents that thermal plume from flowing over PLCs, HMIs, and safety devices down below. This improves component longevity and reduces thermal stresses on those electronic components. The primary side of a control transformer typically carries 480 to 600 volts. Placing the transformer near the top allows those higher voltage feeders to enter the enclosure and terminate quickly, reducing conductor length, minimizing clutter, and improving segregation between high voltage and low voltage wiring. Mounting the transformer high creates a natural vertical separation, high voltage at the top, low voltage control wiring down below. This aligns with good panel building practice, improves safety, simplifies troubleshooting, and keeps the 120 volt and 24 volt DC control distribution clean, organized, and separated from 480 or 600 volt AC. For larger control transformers installed inside the control panels, if thermal considerations are critical, then consider installing over temperature protection. Thermal switches or thermostats embedded in the transformer winding wired for alarm only. This is preferred for process continuity, or trip the main control circuit through the safety controller, causing machine shutdown. Thermistors like PTC or NTC can be embedded in the windings to allow for continuous temperature monitoring in the PLC using an analog input. Per UL 508A requirements, transformer over temperature protection is not mandatory for control transformers below 10 kVA, but it's a good engineering practice depending on application. Next, let's talk about transformer nameplates. The nameplate provides information about its manufacturer, electrical ratings, cooling, and operational limits, serving as the transformer's identity card for safe installation and operation. It's not just a label, it's the transformer's passport, birth certificate, and operation manual condensed into a single weatherproof plate that is affixed on the transformer's body. This is a nameplate for a control transformer that I used in one of my projects. This part identifies the company that designed and built the transformer. This is the manufacturer's catalog number that identifies this particular configuration and the serial number for this specific unit. The power rating is 3 kVA and this unit is designed to operate on 60 Hz system. This is a 3-phase isolation transformer. This means that it has separate windings on its primary and secondary side, which provide galvanic isolation. This distinction is made to distinguish it from another class of transformers called auto transformers, which we did not cover in this tutorial, but they have no galvanic separation. This is the enclosure's NEMA rating. 3R means that it is made of weather-resistant steel and is designed for outdoor use to protect against falling rain, sleet, snow, and external ice formation. The ANC notation describes the cooling method and stands for air natural cooled. This means that the transformer is probably encapsulated or potted in a resin and is designed for harsh outdoor environments. This indicates the internal winding resistance and is crucial for calculating short circuit current availability and voltage drop. AT is the maximum allowable ambient temperature and indicates the thermal design baseline for this unit. Because this is a sealed, non-ventilated enclosure, it is engineered to safely sustain internal operating and surface temperatures up to 135 degrees Celsius. The temperature rise value of 115 Celsius indicates the maximum temperature increase allowed above a standard ambient temperature when running at full capacity. BIL stands for Basic Impulse Insulation Level. It means that this unit can withstand transient voltage surges like lightning strikes up to 10 kilovolts. This one is obvious, it's the physical weight of the unit. This is the most important information on the nameplate, as it describes the voltage rating for the primary and secondary windings, as well as the configuration type. This unit has a 440 volt 3-phase delta primary winding and a Y secondary rated for a 3-phase 208 volt line to line or 120 volt line to neutral. Finally, this graphic shows the primary and secondary windings with terminal markings. The small line drawn inside the H1 corner of the delta triangle indicates that the primary winding feature adjustable voltage tabs. As shown in the table on the left, this allows electricians to manually configure the jumper settings between taps 1, 2, or 3. This changes the internal winding ratio to compensate for high or low supply voltage, ensuring that the secondary supply remains stable at 208 volts, even with variations in input voltages. Control transformers are one of those components where the details actually matter, and now you have them. Today we learned how to size a transformer correctly, how to protect both sides of the transformer as per code, and how to confidently read and interpret the transformer nameplate. If you found this video helpful, then please hit that like button and subscribe to ControlX Automation for more in this control system design series. Drop your questions in the comments. I read each and every one. I'm Akil, and see you in the next one.